Hello and welcome back. Let us try to understand now how decision trees overfitting can be controlled by pruning the trees. So decision trees split the data until it ends up with few sets that we have seen it. Sometimes it splits the data in such a way that the leaf nodes come with only one record. So this is not good. It may not generalize well, and the model may not work in test set and other environment. If you look at our tree, it happened such way, that way only. See this, these two nodes, leaf nodes have got only one record. That means only for those records it will work, and the other records it may fail. Okay. With the size of the tree model overfits. This is one concept, right? This is one statement. With the size of the tree, the overfitting increases. Okay. So if you look at this particular diagram, tree size, number of nodes. If number of nodes are increasing, the overfitting is increasing. On train set, the accuracy is good, and the test set, the accuracy is falling. So this is called as overfitting, and overfitting is directly proportional to the tree size or the number of nodes in the tree. Okay. To avoid overfitting, we can do pre-pruning. Pre-pruning means before we make the split, we'll do chi-square test and see whether the split is significant or not. The null hypothesis is going to be the split is not significant, and then we do chi-square test and see whether it is significant or not. If it is not significant, we will not do that. If it is significant, then only we will do the split. Okay. So that is pre-pruning. That's called as post-pruning. We build a complete tree and then pretend that a particular node is removed along with those leaf nodes, and try to test it. And if the model is working good, better than the original model, then we will remove that node and keep that tree as it is, and again try with another sub node. We'll remove that and again try to test it. If the model is giving more accuracy, then we'll remove that particular node and the leaves and keep the tree as it is. If not, we'll leave it as it is. We'll keep it connected, right? So like that, it is post pruning. So these two are approaches to fix overfitting. The third approach is cost complexity pruning. This is like a regularization, right? There is a concept called the overfitting is directly proportional to depth or number of leaf nodes. Depth means the size of the tree or number of leaf nodes. If you look at these two, right? Condition, and there are many leaf nodes here. There are only two leaf nodes. This is complex, may cause overfitting. This is not so complex and may reduce overfitting, right? So leaf nodes are directly proportional to overfitting. That is the concept. So the cost complexity pruning adds a term to the error, right? What is error? When you pass the train set and or test set, calculate the error, there will be some gap between the actual values and the predicted values, right? So to that we add the additional term alpha into L of t. What is L of t? The number of leaf nodes in the tree. If the number of leaf nodes are, when you actually increase alpha, the number of leaf nodes, it will automatically try to cut short so that the cost will reduce. When you decrease alpha near to 0, you will get almost all the leaf nodes present in the tree. So that's how you can play with the alpha and find the best model where it gives good accuracy on the train set and test set. I haven't seen implementation for this cost complexity pruning in scikit-learn, but R language we have it. So that's about the trees and overfitting and how to actually control overfitting. Reduce the number of leaf nodes and reduce the height, leaf node sample size. These are all hyperparameters in the decision tree algorithms, and we'll play with them. So summary of decision trees is decision trees have really faster learning compared to other methods. Easy to understand because they are if-else conditions, and then information gain ratio and Gini index are the most common methods of feature selection. Tree pruning is necessary to remove unreliable branches. No formal distribution assumptions. There are no assumptions on the data. Can automatically fit highly nonlinear interactions. We'll see this in random forest. Automatic variable selection, right? They whatever the impurity measures are actually variable selections. Handles missing values. Even though missing values are there, no need to impute them before you build a model. Unstable. If you add a little more data, remove data, right, the algorithm completely changes. The tree structure completely changes and the results will completely change. Scalability is an issue for larger data set because the tree gets constructed in memory. It is a big issue to work with huge volume of data. Okay, so that is about the decision trees. We'll try to implement this using decision tree classifier from scikit-learn in coming class. Thank you.